Good morning, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm the host for today's session. Before I introduce our guest speaker for a topic that I find fascinating, I wanted to conduct our poll questions as we are in the habit of doing, and thank everybody for attending. So let's start with the first poll question. And I apologize in advance for any spelling issues that I may have. The question is, which type of interrupters are you familiar with? Just trying to get some feedback from the audience to see what the exposure you've had prior to this and probably where your interest may lie. So it looks like we have a quorum participating, and I appreciate that. Here's how folks have weighed in on the topic. It looks like we're pretty heavily involved with people that know what they're doing, which is good. So the second question is, have you had troubles with interrupters within the recent past? Looks like we've got a quorum here on this question. And here's how people have weighed in. Again, thank you very much for participating. Our guest speaker today is Jerod Day. Mr. Day received his BS and master's degree in mechanical and energy engineering from the University of North Texas. He's head of engineering at Vacuum Interrupters, who specialize in design, testing, and manufacturing of vacuum interrupters. Jerod, you have the podium.
Thank you, Jim. All right. Like Jim said, my name is Jerod Day. I'm the head of engineering at Vacuum Interrupters, Inc. And our main business is supplying vacuum interrupters for circuit breakers that are no longer supported by the manufacturer. If you have a failure on one of these circuit breakers and you were to call the manufacturer, they would suggest buying a new replacement or a retrofit breaker. And what we do is supply new replacement vacuum interrupters that have been re-engineered with the newest technology in vacuum interrupters, and supply those so that the circuit breaker can continue to operate as it has until the mechanism reaches its end of life. So today we're going to be talking about addressing and mitigating circuit breaker vacuum interrupter failures, and specifically related to the vacuum level inside. So I'm just going to go over a brief history about vacuum interrupters. The idea for using vacuum as a medium for interruption was proposed in the 1920s, but there was many problems around that time, the Depression and war. So the idea really didn't take off until the 1950s, with different electrical manufacturers doing research. In the U.S., there was General Electric and Jennings High Voltage were two of the key players in development of the vacuum interrupter technology. But as far as reaching the industry, it really didn't start to pick up until the 1970s, and from the 1970s began to replace other technologies, air circuit breakers, oil circuit breakers, and SF6 circuit breakers in some cases. And they increased in popularity through the 1980s, where there was a very large boom in vacuum interrupter technology and its use in the industry. So since that time, and still today, most vacuum interrupter manufacturers have a design life for their interrupters of approximately 20 years, at least 20 years. Some even say 30 years. And since that boom, there have been millions of vacuum interrupters put in service, and there are tens of millions in service today. And many of those hundreds of thousands of those are more than 20 years old, so they have actually exceeded their original design life. So we're beginning to see an increase in the number of failures out in the field. So the basic design of a vacuum interrupter, you have a fixed copper conductor, and then you have a moving copper conductor, which is sitting on what's called spring bellows. Those bellows are generally made of very thin stainless steel, between 5 and 7 thousandths of an inch thick generally. Those spring bellows allow the moving copper shaft to open and close, providing a gap to interrupt the current. There's also the contacts, which are attached to those copper shafts, which are generally made of some type of copper alloy that allows for interruption and also to prevent welding. So there are different alloys that help to prevent that. You've also got the external insulation, which is provided by the ceramic body. In this case, older vac interrupters use glass, but those were susceptible to other issues. Now, pretty universally, you'll see ceramic bodies being used. There are also a series of what are called metal vapor shields inside the vac interrupter. So these shields are very important because over time, metal vapor will be deposited from that interruption of the electrical arc, and that metal vapor, if the shields weren't there, could potentially be deposited on the inside of that ceramic body, which is providing the insulation. So if enough metal vapor collects on that ceramic body internally, you would have an internal short circuit. So those shields are there to act as a barrier and to be a place that metal vapor can be deposited, that prevents it from being deposited on the ceramic body. So there are several causes of vac interrupter failure. The most prevalent is contact erosion. Over time, as you interrupt current, a small amount of the contact material is vaporized. So for normal rated current, this is a very slow process. You should be able to operate for the whole life of the vac interrupter, which is generally between 10,000 and 30,000 operations before reaching the end of life at normal rated currents. However, fault currents drastically increase the amount of copper material that is removed from this surface. So it also depends on the application. So what type of application it is can change the rate of erosion as well. So certain applications like an arc furnace, where circuit breakers are operated like contactors, that can cause the erosion to drastically increase. On those circuit breakers, vac interrupters are generally replaced every single year for that reason, because the contacts have eroded so much that the actual length of the VI is reduced. And when the length of the VI is reduced, it reduces the wipe spring pressure or closing force of the vac interrupter. So at a certain point, if that wipe spring pressure is reduced too much, then the vac interrupter won't be able to hold itself closed if it were to see an increase in current. So If that were the case, then you would have a failure, which could be catastrophic. So one thing about this contact erosion is it's a measurable thing. All vacuum circuit breaker manufacturers will specify some way of determining the amount of contact erosion. In many cases, it's a measurement where they give you some starting measurement and then end of life measurement where if it reaches that point, the vacuum interrupter needs to be replaced. Some manufacturers have some type of visual indication, whether it be on the wipe spring itself or sometimes there is an actual physical dot or mark put on the moving shaft of the vacuum interrupter, where when that dot or mark actually recedes inside of the vacuum interrupter when it's in the closed position, then that vacuum interrupter needs to be replaced. But again, this is something that's measurable and can be tracked over time and replaced when it reaches that point. Another cause of failure is the mechanical life. So those spring bellows that we talked about before are rated for a certain number of operations. So this is highly reliable, but occasionally, depending on the application, sometimes they can exceed these number of operations. Circuit breakers generally don't reach the full number of mechanical operations, but contactors, on the other hand, which are operated many times a day, usually can reach this mechanical life. So there are certain factors that can reduce that mechanical life, such as salt air. If you're near the ocean and they're exposed to the salt in the air, then that can cause corrosion, and any type of corrosion could reduce the life of these bellows. Other things such as some type of acid or other type of corrosive environment will also reduce its mechanical life. So, but barring the environmental factors, this is something that's measurable as well. So most circuit breakers have a operations counter on the front. So these number of operations are known, and contactors and the controller can electrically count the number of operations. So again, this cause of failure is something that's measurable, and it can be replaced before it reaches the point of failure. So what we're interested in today is vacuum loss. So over time, the vacuum inside of a vacuum interrupter degrades. It doesn't matter how well you seal it, the vacuum will still degrade over time. The one thing that most people think about is gas permeation from the outside. So even though this container is made of stainless steel and ceramic, it is still possible for gases to diffuse through those materials, mostly very, very small gases like hydrogen or helium, which can have some effect on the vacuum interrupter if there are issues, such as a long path leak through a braze seal or something of that nature. But generally, gas permeation doesn't cause the failure of the vacuum interrupter. There are other things called virtual leaks. So a gas permeation would be a real leak, where gas is actually going from the exterior to the interior, whereas a virtual leak can be a couple of things. There are gases trapped inside of the materials that the vacuum interrupter is made of. So when you put these materials into a vacuum, those gases can begin to leak out of the material itself. So this is called outgassing. So over time, you have a pretty steady rate of outgassing from the materials that the vacuum interrupter is made of. So you have to be sure that the materials that are used are very high quality, and you want to use materials that have an extremely low gas content. Different surface finishes can actually affect that outgassing rate, such as electropolishing or other types of treatment like that. Another type of virtual leak would be a trapped volume of gas. This could be something between a braze joint if two parts weren't properly seated and the joint was able to seal but trapping gas at the same time. Those pockets of gas can be released after a period of time of interruption or melting inside of the VI, and that could cause a drastic increase in pressure. One of the problems with vacuum loss is that the accepted test for determining vacuum loss can't tell you exactly how close to failure you are. It can only tell you right now at this moment failure has or has not occurred. And so up to this point, the vacuum has been a mystery, and there have been lots of attempts at determining the vacuum. Some people try to trend DC leakage currents, and there are other methods that people have tried, but they're not reliable, and there's not been a real consensus on it. So, and of course, there are other causes of failure. Exceeding the ratings of the circuit breaker, cleanliness of the circuit breaker. I've personally seen 20-year-old distribution breakers that had failure, and when they opened the high voltage cabinet, the vacuum interrupters were completely covered in dust. And looking at the maintenance log, the high voltage cabinet hadn't been opened since it was originally commissioned 20 years before. So cleanliness is an important thing with regard to vacuum interrupters and making sure that they operate properly. So going back to the vacuum, I've got a graph here which is called a passion curve. So this passion curve shows the dielectric strength of dry air in this case as a function of pressure and the contact gap. So for this particular graph, the contact gap is assumed to be 1 centimeter or 10 millimeters. And you have pressure on the x-axis. So on the far right, or I have a few red lines here for reference. On the far right is atmospheric pressure, around 1 times 10 to the positive 5 or 100,000 Pascal. As you pull a vacuum, you can see that a very slight vacuum actually has very poor insulating ability. If you've ever tested a vacuum interrupter that failed and you can't even apply voltage to it, I've had some that wouldn't allow me to apply even 1,000 volts. So in that case, then the pressure inside the vacuum interrupter is somewhere in that very low range, just below atmospheric pressure. But if you continue to decrease in pressure, increase in vacuum, there is a drastic increase in the insulating ability of the vacuum or of dry air, starting around 10 Pascal and continuing to increase to around 0.1 Pascal, or 1 times 10 to the minus 1 Pascal. So the left two red lines are basically the operating range of a vacuum interrupter, with the far left red line being approximate pressure at which most vacuum interrupters are sealed when they're new. So the pressure, the difference between a high pressure interrupter and a new vacuum interrupter is about 10,000 times difference. So with normal testing techniques, or high-pot test, vacuum integrity test is the general name for it, it would tell you that you are either in the operating range or outside of the operating range. But that's all the information that it gives you. It doesn't tell you exactly where at in that range that you are. So when these vacuum interrupters were developed and manufactured, the manufacturers needed a technique for measuring the vacuum inside. And the way that they do that is with the pinning discharge principle. So in the pinning discharge principle, you apply a high DC voltage across the open contacts of the vacuum interrupter. Just doing that, nothing happens special. It's just like a DC high pot. You have some amount of leakage current. That leakage current corresponds to electrons that are traveling from one contact to the other through the vacuum. But if you apply a very strong magnetic field while you're applying this high DC voltage, then those electrons and charged particles become trapped in the magnetic field itself. So what that does is it ionizes the gas molecules inside of the vacuum interrupter. And when a gas molecule is ionized, it releases its own electrons. So the effect is an increase in the measured current across the vacuum interrupter. So you have that leakage current, just normal when you're applying the DC voltage, but then you get an additional current, which we call the ion current, that's generated inside of the vacuum interrupter by those gas molecules. So this ion current is proportional to the number of electrons that are released, and the number of electrons that are released is proportional to the number of gas molecules inside, and the number of gas molecules inside is proportional to the pressure. So this pressure is directly proportional to the current that's measured. Manufacturers of vacuum interrupters call this the magnetron test. They call it the magnetron test because when you couple a high DC voltage with a magnetic field and you trap these charged particles, it in essence becomes a magnetron inside of the vacuum interrupter. So the relationship between that measured ion current and the actual pressure inside of the vacuum interrupter can be determined through experiments like you see here, where we have a vacuum interrupter with a vacuum fitting welded onto the end cap. We have a pressure sensor and some insulation so that we can apply the high voltage to the vacuum interrupter while it's being pumped by, in this case, a turbomolecular vacuum pump. So we pump the vacuum interrupter down to a known pressure. We perform this magnetron test on it, and we get a current measurement. So as the pressure changes, the current measurement changes, and we can record these values, and after the experiment we can generate a curve, which is what we call them, of this ion current versus pressure. And so in the future, this experiment won't have to be done. We can simply measure the ion current of the vacuum interrupter and know that the internal pressure is whatever this curve says. So as an example here, most people have never seen a factory magnetron. This is from a European vacuum interrupter manufacturer. This is actually the smallest factory magnetron that I have ever personally seen. Most are considerably larger, about the size of a stand-up refrigerator deep freeze. The test that's performed at the factory requires that the vacuum interrupter be removed from the circuit breaker because they're testing them directly off the line. They have them loose and easy to test. So they simply open the contacts of the vacuum interrupter, place it inside of this device, and do this magnetron test that we talked about. One of the problems with applying this to testing vacuum interrupters in the field is that this device is not portable. It has a very large power requirement because they're applying a constant magnetic field, which requires a pretty large transformer. And also the vacuum interrupter has to be removed from the circuit breaker, which in most cases is not an option during maintenance and testing. Also, you risk doing damage to the vacuum interrupter by removing and replacing it. So we, in 2011, began to develop a portable test set for doing this magnetron test, and the name we came up with was Magnetron Atmospheric Condition Test Set, or MAC test for short. So our MAC tester can test vacuum interrupters while they're still installed in the circuit breaker because of our special coils that we developed for supplying that magnetic field. It's very portable. The test set itself weighs about 50 pounds. And the way that we were able to reduce the weight so drastically is we turned the measurement from a constant measurement like a manufacturer would use to a pulsed measurement. So instead of having to constantly supply current to a magnetic field coil, we are charging a bank of capacitors and rapidly discharging that bank of capacitors to the magnetic field coil, which provides a very strong magnetic field for a very short period of time, but long enough for us to do this measurement. So I get a lot of questions when I do this presentation about high pot testing or vacuum integrity testing versus a MAC test. And so I just want to stress that a MAC test is not meant to be a replacement for a vacuum integrity test. I still do this test on every circuit breaker I do. It's the be-all, end-all test, vacuum integrity that is, that tells you whether or not the vacuum interrupter is still good or whether or not it has failed. The only problem with vacuum integrity, again, is that it doesn't indicate the level of vacuum inside. So you could be days away from failure and still get a passing result. Also, it's not trendable over time, so you don't see a degradation in these results as the vacuum degrades. Whereas with the MAC test, it's supplementary to the high pot test. So it actually gives you a data point that you can put on this passion curve and see that data point move over time as you retest the vacuum interrupter during your normal maintenance cycles. And so we know the approximate point of failure with regard to pressure for these vacuum interrupters. So when that data point approaches this point of failure, then you have time to plan for replacement and plan to replace it before failure occurs. Not only that, over time, as more tests are done on the same vacuum interrupter, those data points can be trended, and extrapolated to give you an estimate of when that failure point would be way ahead of time. Our magnetic field coils that we have with our MAC tester, this is the most common. It's what we call the universal flexible coil, or flex coil. It fits most applications. The coil has to be wrapped around the vacuum interrupter at least 5 times. Doesn't matter the size of the vacuum interrupter, as long as you can get 5 wraps. Then this coil can be used for supplying that magnetic field. And the connector is what allows for this magnetic field coil to be wrapped around the vacuum interrupter while it's still installed. So basically, this coil is just a bundle of 50 wires, and on the connector, each pin is offset by 1. So when you connect it together, it makes a continuous circuit from input to output, and so each wrap is actually 50 wraps. So with those 5 wraps, you're in essence getting 250 wraps of this wire around the vacuum interrupter. We also have lab-based coils or shop-based coils. If you are a service shop or you have the vacuum interrupters removed from the circuit breaker often, then this would be a coil that would make the test much easier. You don't have to wrap it. You simply open the contacts of the vacuum interrupter and place it inside of this magnetic field coil. It's highly consistent, whereas with the flex coil, there is some possibility of human error, of not wrapping the coil in the exact same place, which doesn't give a very large change in the result, but it's just not as consistent as this fixed coil could be. And these have adjustable bases so that you can adjust them for different length vacuum interrupters, because you do want to place the magnetic field around where the contacts of the vacuum interrupter are. And then we have some special application coils, which we call rigid coils. These are for applications where these type of fixed coils can be used. In most cases, they can't be put around the vacuum interrupter because of a line to load insulator or an insulator connected to the frame. But in this example case, we were able to make a custom fixed coil that fits directly over the insulation of the circuit breaker and makes the test much quicker. The only thing with these larger coils is that because of their size, they require additional capacitors, which we call a cap box, which is additional, that's connected to the MAC tester to provide the additional power that's needed to create a sufficient magnetic field. So I have a few case studies of this MAC tester. And this graph is results from testing 300 of the circuit breakers that we have in stock at one of our affiliate companies, Circuit Breaker Sales. And what you see is they're divided into a few different categories, where we have green would be a good pressure or new pressure. B would be a midlife pressure. C would be approaching the point of failure, and D would be when it either fails our test or fails high pot test. And on the x-axis, you can see the age of the circuit breaker that were tested. So all of these were the exact same type of circuit breaker that were manufactured over this 40-year period. So we were able to test new versions of the circuit breaker, as well as some that were as old as 40 years. And what you see is somewhere between 30 and 40 years, there's a drastic increase in the number of vacuum rippers that are near failure as well as failed. So this matches well with our experience that the original 20-year shelf life suggested by the manufacturers was pretty conservative, and in reality, these vacuum rippers can last well over that 20 years. The average now that we're seeing is about 35 years for those original circuit breakers. And so again, the boom was in the 1980s, so we're well past that 35-year mark, and are seeing these failures now. So another case study was a power plant in Central Texas. They had approximately 100 of the exact same type of circuit breaker, and all of their circuit breakers were manufactured within 1 month of each other, between December of 1985 and January of 1986. We began to market our MAC tester in 2011, which coincidentally is when this power plant had their very first vacuum ripper failure. They didn't think much of it. Just a few months later, they had their second vacuum ripper failure, and this is since those circuit breakers were installed. So this made them very worried, and they contacted us and asked us to come and test all of the circuit breakers that they had of this type. And we spent several days at the site, and we tested every single one of these circuit breakers. And what we found was that there were 8 of those circuit breakers which the MAC test identified as having high pressure and being near the failure point. And so those were tagged for replacement, and spare breakers were put in their place. And as far as I'm aware, they have not had any additional failures. Another case study was a contactor manufacturer who did not manufacture their own vacuum eruptors. They were buying these vacuum eruptors from an international supplier, and they were seeing a very high failure rate out of the box on these vacuum eruptors. And in a lot of cases, they were able to catch them in their own QC testing, but many of them reached the field, and their customers were seeing failures on their contactors. So this was a very big deal to them. So they reached out to us about our MAC test set because they had suspicions that it was related to the vacuum level inside. So they purchased a MAC test set and put it into their QC program, and they identified approximately 10% of these vacuum eruptors that they were receiving were at a very high pressure near failure when they were receiving them from overseas. In talking with their manufacturer, they determined that one of the conditioning processes that they were doing on these vacuum eruptors after they were manufactured was doing damage to the inside of the vacuum eruptor and causing an accelerated leak rate inside. So after this was determined and the problem was corrected, they purchased another MAC test set from us and sent it to their manufacturer to be tested before they shipped the VIs. And so in that time, the failure rate of their contactors has dropped dramatically, and last I heard it was less than 1%, but it could be much better. So MAC testing itself provides the final piece of the puzzle for testing vacuum eruptors. Most of the failure methods are either measurable, meaning that you can train them over time and replace the vacuum interrupter before it reaches the point of failure, or they're preventable, where things such as cleanliness can be done during normal maintenance to prevent that. But until the MAC tester, there was no ability to accurately determine the level of vacuum inside of the vacuum interrupter before failure. So this MAC tester provides the final piece of the puzzle with regard to vacuum interrupter testing. A new development with Vacuum Interrupters Inc. is that in the course of developing our MAC test set, we've done research on other ways to apply this, and we found that we can actually improve the level of vacuum inside of the vacuum interrupter electrically using similar principles. So the way that this works is we apply this high voltage, and we're ionizing these gas molecules. If you can supply enough energy to these gas molecules and accelerate them with enough energy, then you can actually cause them to be permanently either embedded in materials inside, or cause them to react with materials inside, such as the copper or the stainless steels, and turn into a copper oxide or a carbide, becoming a solid and no longer contributing to the vacuum inside. And so we found that we can take a vacuum interrupter that is very near failure and bring it down to somewhere near midlife, which is equivalent to adding somewhere between 5 and 10 years of life to these vacuum interrupters. Right now, we're in the middle of a few case studies on this, where with our local utility and some other large factories that use many of these vacuum interrupters. And so this vacuum interrupter conditioning can be applied to any vacuum interrupter that can be MAC tested. So if a MAC test can be performed on the vacuum interrupter, then this vacuum interrupter conditioning can also be performed on the vacuum interrupter. And we're not sure. Our goal is to increase the life of a vacuum interrupter to the same level as the life of the mechanism. So we're not sure how many times we can apply this conditioning. It's possible that we can do it multiple times over the life of the vacuum interrupter, bringing it from close to failure back down to midlife. So we're excited about this development, and I'll let you know more in the future. But Jim, that's all I have today.
Thank you.
I appreciate the time, and let me know if you have any questions.
And like I said, I find this fascinating just because of the background I have in vacuum physics. The only question that came in, we'll kind of leave it open for a couple minutes, was a verification of the negative pressure that's in a typical vacuum interrupter. You showed a graph. Mm-hmm. What's the limit on, or what's the range for the negative pressure?
The general range, we're in pascals here, so somewhere between 10⁻⁻⁻ Pascal down to 10⁻⁵. So that would be 0.1 Pascal down to 0.00001.
Excellent. Thank you, everyone, for attending today. Thank you, Jerod, for a very informative presentation. And I think we're getting several attaboys coming on the question line. So have a good day, everyone. And Jerod, we'll be talking to you down the road.
All right. Thank you, everyone. Thanks for the time.